Okay, so today we're going to take a look at absolute value convergence. The kind of flip side to absolute value convergence is what we call conditional convergence. Which at first doesn't seem like a big deal. It's like, huh, so what? But it actually has an interesting extra thing attached to it. My favorite test ever is the ratio test. And then we'll also take a look at the root test with a few problems. And I think once you get used to the ratio test, you will like it too. You think it's pretty cool? Good. All right, so let's take an example of a series. So let's look at the sum as n goes from 0 to infinity of, how about -1 to the n divided by 2 to the n times n factorial. We haven't seen factorials yet, which is one reason the ratio test is going to come in handy. So when you have a new series, it's always a good idea, especially if there's new stuff in it, to list out some terms, get a feel for it. So let's do that. First term, so this is kind of a trick question. If you haven't seen factorial before, 6 factorial means to take 6 times 5 times 4 times 3 times 2 times 1. So an example of this formula in action is my wife asked me to clean the living room the other day, which meant cleaning up the bookshelf. When I was cleaning up the bookshelf, I had these 6 books to put in a specific spot on the bookshelf. And at first I just threw them in there, and then I'm like, no, I can't just throw them in there. I should put them in order by author. Well, when I'm doing that, usually the author says, like, you know, David Johnson. I was like, I put him in by author's first name. I'm like, no, you put him in by author's last name. But then I looked at it and the sizes were all wrong. So I decided to put him in from, you know, tallest book to shortest book. And then I just started thinking, well, how many different ways could I put these 6 books back on the shelf? And the first spot on the shelf, I had 6 options to pick a book from. Once I throw it on the shelf, there's now 5 books left. So the second place, I had 5 options. So how many options altogether did I have? Well, let's see. 5 times 2 is 10. 6 times 4 is what, 24? Times 3 is 72, so that's 720 choices. So you imagine, I was there at the bookshelf for a while, not getting the house very clean, but I was having fun. So that's factorial. The rearrangement of things like that is called a permutation, okay? So anyway, factorial. Other things about factorial, basically it means multiply by every counting number down to 1. But what is 0 factorial? Well, for convenience, a bunch of math people said, let's make it 1. Doesn't make any sense. It does in some other weird way, but we're just going to go with it. It's 1. So you might say, why is he starting off at 0 here? That's not a good idea because we're dividing by n, but we're dividing by n factorial, which 0 factorial is 1. So anyway, long story short, my first term is 1. All right, so then for my second term, oh, I lied. No, I didn't. I told the truth. For my second term, I'm going to get 1, -1 to the 1, so it's going to be a minus on that one. And then 1 factorial is just 1, nothing big there. So my next term is a -1/2. And then I'm going to have a plus because I'm jumping over to n equals 2. And that's going to give me a 1 over 4 times 2 factorial. 2 factorial is 2 times 1, not 21. 2 times 1. And then the third power will be negative minus 1 over 2 cubed is 8 times 3 factorial, which is 3 times 2 times 1. So you kind of get the idea of this series. What's your perception about the denominators here? They're getting big fast, right? So I think just looking at this, I can say, hey, this looks like it converges, Okay, so we have that intuition by just looking at the terms. So now we're just going to prove it in a couple of different ways. The first thing I want to apply to prove it is the alternating series test, because that's a super easy one. All you have to do is look at it and say, all right, does it alternate strictly every other term? Answer, right there, yes. Then what I have to do is show that ignoring the sign, do the individual pieces go to 0? So let's go to the next page. So we have the alternating series test. And let's see, what else do we have here? We have our b sub n's. Ignoring the sign would be 1 over 2 to the n times n factorial. And I need to take the limit as n goes to infinity of 1 over 2 to the n times n factorial. And this one is pretty straightforward. We know the denominator is growing while the numerator is fixed. So this does go to 0. So that's condition 2 for the alternating series test. Condition 1, it does strictly alternate. Due to that negative 1 to the n factor. And so now we definitely have convergence. So we have convergence. Next thing we're going to look at is we're going to say, well, what about the absolute value of the terms? Does it converge in absolute value? All right, so, absolute value convergence means to explore this series. And the absolute value just says, hey, if there's any negatives, forget about them. So this is exactly equal to the series as n goes from 0 to infinity of 1 over 2 to the n times n factorial. Okay, so this is a new series. It doesn't alternate anymore. We lost the cancellations. So first thing I do to a series like this is I think, okay, can I apply the divergence theorem to this? And we just checked a minute ago, do those guys go to 0? And they do, which means the divergence test tells me nothing. Okay, so I'm just going to make a note. I thought about the divergence test. And it was not helpful. Evidence of that is on the previous page where we thought about this limit. All right, what else do we have on our side here? We have our comparison tests, right? We have the direct comparison, the limit comparison. Have we ever seen anything with an n factorial in it before? No, so it's hard to find something similar to this. But let's think for a minute about a comparison. That what comes to mind to me for a comparison. Oh, somehow I lost my pen. Interesting. There we go. For a comparison is ignoring the n factorial. What kind of series is that? Excellent, geometric. So, is it convergent for geometric? Yes, good job, right? Because I could rewrite it as the sum as n goes from 0 to infinity of 1/2 to the n. So this is geometric. R is equal to 1/2, which is less than 1. Is that me buzzing over here? I'm sorry. It's my eye doctor. You with me? Okay, so so it's convergent. Is this new series here? Are the terms, the little pieces, bigger or smaller than those guys there? Smaller? Which one's smaller? The new series is bigger, right? So what I can say is I can say that 1 over 2 to the n times n factorial is less than 1 over 2 to the n. This guy is convergent. So the new things, the unknown stuff, is always smaller than convergent terms, right? I made the denominator bigger, which makes the whole fraction smaller. Is that a good thing for direct comparison? Yeah, it's a good thing because basically I have a squeeze theorem going on. These guys here always sit underneath those guys right there. This one converges. So what we have is by direct comparison, my sum as n goes from 0 to infinity of, it was originally the absolute value, which stripped those signs there, converges. Now, this tells me a couple of different things. The book says that means this, my original series without the absolute value with the alternating sign in there, it's called an absolutely convergent series. Again, I've voiced my dissent. I don't like the phrase absolutely convergent. It's convergent in absolute value. Okay? The cool thing about being convergent in absolute value is, so this is again what they call absolutely convergent. Absolutely, which just always never sounded right to me. Always never. It's a nice combination of words. What we really mean is convergent in absolute value. So the cool thing about sequences that are convergent in absolute value, which is this original one here with the alternating signs, is that you can rearrange the terms all day long and it converges to the same place. Be like, what do you mean? Whenever you add numbers, you can rearrange the numbers. But the infinity thing can cause weird crap to happen. So there are some series that are not convergent in absolute value. Okay, so just a note here, we can rearrange terms because it converges in absolute value. An example of a sequence that this didn't work so well for, sum as n goes from 1 to infinity of -1 to the n plus 1 over n. We determined that this was convergent by the alternating series test. On the other hand, if I strip the signs, then I end up with the harmonic series, which is divergent. If the absolute value of the terms is divergent, but the original series is convergent, then we say this original series is conditionally convergent. What do you mean conditionally? Well, on the condition, we don't mess with the signs. That's all. We don't mess with the signs, it converges. The other thing that is a condition here is we can't mess with the order of the terms either. A while ago, people discovered that if you do change the order of the terms in a fixed pattern forever, you get a different answer in the end, which is very troublesome. We don't want things to change answers. If you have a finite amount of terms, we know, right, addition is commutative. You can add them in any order you want. But if they're infinitely many, and they change sign, then you can change the order and get a new sum every time. Well, sometimes. You have to be clever about the rearrangement. Okay. So I'll show an example of that later. I don't have time today. But that's the big thing about absolutely convergent versus conditionally convergent. If the series that changes sign is not convergent in absolute value, that means you can't mess with the order of the terms. Otherwise, you might get a different answer in the end. Okay. And I don't know about you, when you add, isn't it nice to change the order, make it easier sometimes? Like when you see a 7 and a 3, hey, they make 10, even if they're not next to each other. Okay, so there might be a reason you might want to change the terms, but it turns out if you have an infinitely long series, that can sometimes cause trouble. That's all. All right, so next, let's go to the ratio test. My favorite test ever. So what the ratio test says is, it turns out you can compare a series to itself instead of comparing it to another series. And what you do is, get the order right. Where'd you go? Where'd you go? There you are. Sorry, normally I know this quite well, but it's not my day today. Okay, that's what I thought. So we have some series. Let's say we start at 1 of a's. So there's a first term, and there's a second term, and there's a third term, and they keep on going. And somewhere along the line, there's going to be some nth term, and then there's going to be a term after that, n plus 1, and it just keeps going. And so what you do is you look at the ratio of a term and the term before it. So I'm going to say let our term be n plus 1. The term before it would be a sub n. Okay. Alternatively, you could do n and n minus 1 on the bottom, but this is the way it's usually written. Now, the series could change sign, so we just take the absolute value of it to get rid of any sign changes to simplify it. And then we take the limit of this as n goes to infinity. And one of 3 things can happen. Either this limit right here is going to be less than 1, in which case the terms are getting small enough fast enough, okay, that the new terms are smaller than the old terms sufficiently, and we're going to have convergence. B, the sequence is this ratio is greater than 1 in the limit. Okay, so that means the terms are actually growing, which is a problem. That's divergence. There's a third option when I look at the 1 as my focal point. It could be 1 in the ratio, which means they're growing at about the same rate, and I don't know what's happening. That's inconclusive. Pick a different test. The motivation for this comes from geometric series. So consider one we looked at earlier, sum as n goes, let's go from 1 to infinity of 1/2 to the n. Applying the ratio test to this, I would take 1/2 to the n plus 1 and divide by 1/2 to the n. Now I don't have any alternating signs, so I don't care about the absolute value, but I want to take the limit of these guys. Usually before I consider the limit, I clean up this crazy fraction. Well, I have the same base, right? So that means I can just subtract the powers. N plus 1 minus n is 1, so I get 1/2 to the first power, which is 1/2. And fortunately, the limit as n increases of 1/2, since it's got no n's, is just 1/2. Okay. So that's where it came from. The ratio test is the idea of having a constant ratio between terms, which is a constant base. And it turns out we can use that to figure out how other sequences converge or diverge. So what we're going to do next is apply the ratio test to that series where we just beat the crap out of. And that was the sum as n goes to infinity, from 0 to infinity of -1 to the n over 2 to the n times n factorial. Now I know we already know this converges, but let's just see what the ratio test does with it. Now with the ratio test, remember that's the limit as n increases of the absolute value of some term we usually call a sub n plus 1 and the term before it a sub n. So what I like to do is before I jump into the limit, I just try to say, well, what's happening algebraically inside there first? Okay. Now we know we have the absolute value, so any plus or minus term can be ignored. So I just ignore that and I say, all right, what is this ratio? So that's going to give me 1 over 2 to the n times n factorial. Oh, no, I lied. N plus 1 first. N plus 1 times n plus 1 factorial divided by 1 over 2 to the n times n factorial. Quickly, we're going to realize that since we're dividing by fractions, it's just going to be easier to multiply by the reciprocal of the second one. So this is 1 over 2 to the n plus 1 times n plus 1 factorial times the reciprocal of the bottom one, which is 2 to the n times n factorial over 1. This guy up here? Yeah, so since I'm taking the absolute value, that's just either, the numerator is either plus or minus 1. That's -1 to the power n up there. And so it's not going to contribute here, right? Because the absolute value. So I'm skipping the step where I take the absolute value by just saying, ignore the sign change up there. Which n? This one right here? Well, that's -1 to the power n, right? It's either 1 or -1. And because we're taking the absolute value of anything, it's gone, right? I can put it back in. And then the absolute value says if it's negative, just ignore it, which makes it a 1. You with me now? Okay. Yeah, so usually what I do is the -1 to the power, I just blow it off. Because I'm taking the absolute value, then I don't have to worry about the absolute value anymore. Okay, so then we can clean this sucker up a little bit. So 2 to the n goes into 2 to the n plus 1 2 times, right? Because this has one more 2 in it than that one up there. N factorial is a little trickier. You okay with that one? Okay. I'm going to rewrite that. So right now, I have it rewritten as, pulling it all together, let's see, n factorial over 2 times n plus 1 factorial is all that's left behind from those two. And I'm just going to write out what n factorial means to get a grasp of this. I'm going to pull the 1/2 out. N factorial is n times the number before it, which is n minus 1, times the number before that, all the way down to 2 times 1. N plus 1 factorial is n plus 1 times what's right before n plus 1? N, right, times n minus 1, blah, 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 all the way down to 2 times 1. And so I love the ratio. Here's why I love the ratio test, because I get to cancel lots of stuff when there's factorials. I mean, look at that. N divided by n is gone. N minus 1 divided by n minus 1. 3, 2, 1. Everything divides out, except that one little piece. So what I'm left with then is 1 over 2 times n plus 1 after I clean that up. So I mentioned earlier when I'm doing these, I kind of have a 3-stage approach to it. First thing I do is decide I can ignore any negatives. Second thing I do is I don't worry about the limit yet. I just write one fraction times the reciprocal of the other. clean that up as much as possible, and now finally I'm saying, all right, let's do that limit. Well, this one's not too bad now. The top is fixed at 1, the bottom's getting bigger and bigger and bigger, and so this goes to 0. Let's see, I'm pretty sure that 0 is less than 1. Agreed? So that means we have convergence. Even better, we started off by taking the absolute value of the terms, essentially. Even in the ratio, that means this converges in absolute value. So that means not only is my original series convergent, but if I strip the signs, it's still convergent. Okay, so this first part here tells me that the sum as n goes from 0 to infinity of -1 to the n over 2 to the n times n factorial, it's convergent. But because the absolute value is involved in showing that, I now also, as a bonus, get that the sum as n goes from 0 to infinity of 1 over 2 to the n times n factorial is also convergent. Let's see, convergent. Something like that. Okay, so that's a bonus I get too, because the absolute value involved in the ratio test. So the ratio test is super powerful for a couple of reasons. One, anytime you have powers of n or factorials, it just kicks butt cleaning those up and makes it much simpler. And then two, we often get an absolute convergence in there too. Absolute value of terms converging means that it doesn't matter whether you change sign or not, you still have convergence. So we're going to do another one of these, try and get a hang of it. Okay, let's see, what should we try next? Oh, yeah, that's a good one. Let's try better color. Sum as n equals 1 to infinity of 2 to the n times n over 5 to the n. Okay, so step one, if it's new, list some terms. All right, what's this look like? Let's see. I'm going to get, first term is 2/5. Second term is 4 times 2 over 25, 8/25. Third term is going to be what? 8 times 3 over 125. So let's see, 2/5 and 8/25 and 24 over 125. These seem to be dropping. What would the next one be? See, 2 to the 4th is 16 times 4 is 64. 125 times another 5 is, I think, 625. Those look decreasing to me. Okay, so just what I'm thinking of is the divergence test. Is it true that the limit as n goes to infinity of 2 to the n times n over 5 to the n, is that going to 0 or not? And I'm thinking it is. You're thinking not? Okay, so I could rearrange this to try and think about it a little better. I could, if I'm unsure, I could say, well, because I'm hoping that the denominator is growing way faster than the numerator, okay? Limit as n increases. If I divide top and bottom by 2 to the n, then I'll get n over 5 to the n over 2 to the n. Rewriting that one more time, n over 5 halves to the n. Now 5 halves is bigger than 1, which means this thing is growing. Okay, it's an increasing geometric sequence, not sum, but sequence. Which grows faster, exponential functions or linear functions? Yeah, and we could use L'Hopital's rules to show that. So if I did apply L'Hopital's rule here, it's a fancy L, the derivative of the numerator is 1. The derivative of the denominator, I still got a limit here, is the base, 5 halves to the n, times the natural log of 5 halves. We looked at a similar kind of thing yesterday. So here I have a fixed numerator, denominator is growing out like crazy. So this definitely does go to 0. So I can show that. So it was a lot of work just to say it's a candidate for convergence, but I just don't know yet. Now, with this part in mind right there, I'm thinking this is kind of similar to a geometric series, but somebody threw that extra n in there to mess with me. Okay, so I'm thinking direct comparison. So this is what goes through my mind every time I see a series. I list some terms out. Have I seen something like this before? Can I just say it diverges right away? No, darn it. And then I think, what does this look like that I know, like direct or otherwise? So I'm thinking, well, it looks, so here's my unknown one, 2 to the n over, 5 to the n times n there. How does it compare to 2 to the n over 5 to the n? Well, because I multiplied something in the numerator, the guy on the left is bigger. This guy right here is a convergent geometric series. Right, because I could write it as 2/5 to the n. So r is 2/5, which is less than 1. And it's on the wrong side. My unknown thing is on the wrong side of the inequality. I can't squeeze it down, so that's a problem. So I could look at a ratio, but instead I want to use my favorite one, which is the ratio test. Or sorry, I could use the limit comparison, excuse me, but I'd prefer to use the ratio test. So ratio test says, again, take the absolute value of the ratio of consecutive terms. So limit as n increases of the absolute value of 2 to the n plus 1 times n plus 1. So the thing to be careful of here is everywhere there was an n, make sure you get an n plus 1 in there. Don't miss anything. And instead of dividing by the nth term, I'm going to multiply by its reciprocal. So I'm going to say times 5 to the n over 2 to the n times n. Now there's no negatives here anywhere, so the absolute value really isn't necessary. I can get rid of that in a minute. And then I start killing stuff. So let's see. 5 to the n goes into 5 to the n plus 1, leaving a 5 behind in the bottom. 2 to the n goes into 2 to the n plus 1, leaving a 2 behind in the top. And because of this plus sign here, there's really not much I can cancel there. I'm stuck with the n plus 1 over n. So what do I have left? New page. All right, I think I don't need the absolute value anymore, right? So I got the limit as n increases of 2 times n plus 1 over 5 times n. You guys with me there? And that's just polynomials of the same degree. The leading coefficients take control, and so the limit of this must be 2/5, which is less than 1. And so we have convergence. Convergence. Not only that, since we took the absolute value of those terms as we were looking at it, it's convergent in absolute value. Now that seems kind of lame, so what? Yeah, there were no negative signs. What's the big deal? But again, the big deal is I can rearrange any term in that sum forever and ever and ever, and that won't change the answer in the end. Okay. But if it wasn't convergent in absolute value, we can't mess with the order because that can change the answer, which is weird. That always just blew my mind. No, actually. We will just have to be always cautious about moving terms around, is basically what it means. You can't just arbitrarily move stuff. If you just move two terms, that's no big deal. But if you have a pattern of moving terms forever, that can be a big deal and totally change the answer. All right. All right, let's do one more. The root test, I don't use very often, but I'll just show it here. What's a good problem to show the root test on? Yeah, that won't work. Suppose I had something like the sum as n goes from 1 to infinity of 2n plus 1 over n squared minus 2, all to the power n. This is a rather complicated sucker because I have n's in the base and n in the power. And when we saw stuff like this back in Calc 1, we had to do logarithmic differentiation, which is a nightmare. Well, that's not a nightmare, but it's just a lot of work. If you apply the ratio test to this, it gets nuts fast. So we're not even going to do that. We're just going to go right to the root test. What the root test says, and the root test is also derived from the idea of geometric series, is that if you take the nth root of the absolute value of the nth term of your sequence, and in the limit as n gets big, you look at what happens there, and just like with the ratio test, one of three things can happen. Either this sucker is less than 1, option A, which means we have convergence. The limit is greater than 1, in which case we have divergence. Or it's equal to 1, and we don't know anything. Inconclusive. Find another test. So the root test is particularly useful when you do have a power of n floating around in there. So what we need to consider is what is the nth root of my nth term? So 2n, what was it, minus 1, plus 1, plus 1 over n squared minus 2 to the power n. And what's the nth root of the power n? That gives us a power of 1. So this is just the base, 2n plus 1 over n squared minus 2. Now, I ditched the absolute value, which I guess was a dangerous thing, so I should put it back in. Let's see, where's it go? No, it goes out there, sorry. Because for odd powers of n, this could be negative. You know, for example, when n is 1 in the denominator, I'm going to have 1 minus 2, which is negative 1, which is a problem for the root. Now, I don't really care about the first few terms, because what am I doing? I'm really looking at big n's. Okay. So as long as later on it stops being negative, I'm okay. Well, would you agree if n is greater than or equal to 2, then this is going to be positive, right? Because then n squared is bigger than 2, and I don't have a problem anymore. So I'm okay to ditch the absolute value because I'm looking at big n's. So now I consider, okay, what's 2n plus 1 over n squared minus 2 doing for big n's? It goes to 0, right? 0 is definitely less than 1. So this converges by the root test. It's also absolutely convergent, which means convergent in absolute value, right? Which means I can rearrange the terms if I want. I usually don't want to, but it's a thing. Man, that was exciting, wasn't it? Come on, a little bit. So we won't use the root test a lot, but sometimes it is handy. If you're bored tonight, try the ratio test on that, and you'll be like, oh, he was right. That is a mess. If I didn't have a cold and I got a little more sleep last night, I think I could probably do it in half an hour. I'll try it later if I'm feeling better, but give it a try if you're bored later. Yeah. Instead of, I think it is, but I know I've tried ones like that before and gave up after a while. Yeah, but I haven't tried this one, but I can see what it looks like in my head because I've done enough of them that I'm like, ooh, I don't want to go there today. Yeah. Yeah, because you got n+1s everywhere, right? And n's and reciprocals. This was like, yeesh, it's crazy. And what comes to mind, yeah, never mind. We could go on for half an hour on that one. If you're bored later, take a look at it. So I'll review some of this stuff tomorrow. We're going to be moving on to the second part of this chapter, which is power series. Power series is actually a whole bunch of sections thrown into one. Taylor series is an idea. It's a kind of power series. And that's our real power tool for analyzing series. It's going to take us, we're like, as a kid, you learned to draw circles and squares, and then all of a sudden you learned how to draw like boxes and spheres on a piece of paper. So we're kind of making that leap once we jump into power series. It's like jumping from 2 dimensions to 3 dimensions. Okay. And it's going to be a blast. We're going to learn all kinds of new stuff. And the nice thing power series gives us is it's more than just saying it converges, but I don't know to what. Power series is going to be able to give us the ability to say, I know what you converge to now. Okay. So have a good day. Good luck with differential equations.